which I already know is 1 over n plus 1. So in the numerator, I have n minus k, 1, the product of 1 to n minus k is n minus k factorial. In the denominator, I have, well, if I had 1 up to n, it would be n factorial, but I'm missing the first k term. So this is n factorial divided by k factorial. So that is equal to n minus k factorial divided by n factorial. What is this?
1 over n choose k.
1 over n choose k, exactly. So this is equal to a n k is equal to 1 over n choose k times a n n, which is equal to 1 over n choose k, 1 over n plus 1. And remember, this is the probability of x1, x2. This is what I assume is the probability of x1, x2 up to n. So that's tracing this back. A and k is the result of the integral I had on the other page. That integral was the integral of this probability given theta over theta. So that's the probability that I'm assuming for x1 to xn. So now, if I wanted to create a source code with optimal code word lengths, what I would do is I would take this value. Actually, this is not the true probability. Let's not call that p, let's call that q, because it's not the true probability, it's some other function. So if we wanted to assign a source code with optimal code word lengths using these probabilities, what would those code word lengths be? So the optimal code word length for any given, if I have a source with probabilities, the optimal code word length is log 2 1 over probability, right? So what I want to do is I want to assign code words with probabilities ceiling log 1 over q, x1, x2, and so on to xn. But this is equal to ceiling. Actually, let me get rid of that ceiling. That's less than or equal to log 1 over q, x1, x2, and so on, xn plus 1. Equal to log 1 over n choose k, excuse me, log 1 over n choose k, 1 over n plus 1, which is log n choose k plus log n plus 1 plus 1. This is exactly what we had just before. Remember, we started out with log n plus 1 plus log n choose k plus 2. So this is basically the same expression with just a, I mean, it doesn't, the 1 or 2 in the penalty term doesn't really matter because, again, this is a bound. So we can argue that the lengths in this case the lengths are less than or equal to NH n plus 1/2 log n plus something that's order 1. Using exactly the same derivation that I went from these two terms to there in the last code, because it's basically the same expression except plus 1 instead of, or plus 2 instead of plus 1. So basically, if we start out with this funny probability Q, we don't lose anything compared to our code where we first say K and then we encode based on K. So if I have any coding scheme that needs a probability and I hand it the probability Q, and remember we already have coding scheme, the Huffman code, which is guaranteed to perform within 1 bit of entropy, and the Shannon-Fano-Elias code, which is guaranteed to perform within 2 bits of entropy. If I hand those procedures this Q, then basically I have this penalty and that extra 1 or 2 bits is incorporated into the order 1. So my strategy will be take this funny probability and give it to an existing code word, and I should do pretty well. Yes?
I'm sorry to interrupt again. How did you compare this last log summation of logs to the length formula? You said
Yes.
it's similar to something we saw before?
Yeah, so just now I showed that log n choose k plus log n plus 1 is less than or equal to 1/2 log n plus n hk over n plus some funny terms that were order 1. That's what we just spent the last 20 minutes talking about. So it's exactly the same thing. So I still have this, and that will lead directly to here. So basically I just said it's the same derivation exactly to get to here.
Sorry. Okay, I see.
Okay, now there's a second trick. One might argue, okay, this Q is, maybe it's difficult to calculate. Maybe I can't calculate this Q. So there's a second trick that I can show you. And that trick shows that it's actually easy to calculate that Q. So let's say I have x1, x2, x3, up to xi minus 1. Actually, let's say I have q of that. And then I want to calculate q of xi given x1, x2, and so on up to xi minus 1. Excuse me, I want to calculate q of xi equals 1, given that. Rewrite that. By Bayes' rule, q of xi equals 1 given x1, x2, so on up to xi minus 1 is equal to q of x1, x2, and so on, xi minus 1, and xi, where the xi position is equal to 1, divided by q x1, x2,